This is the fastest ARM desktop in the world. Yes, even faster than the M2 Ultra Mac Pro. And today, I made it even faster. I upgraded everything. Faster RAM, 128-core CPU, 40 series GPU, I did it all, and we're gonna see how much we can obliterate the M2 Mac Pro. 128 cores, that's 5 times more cores. I'm also gonna upgrade this thing from 96 all the way to 384 gigabytes of RAM. The Mac Pro? Sorry, it only goes up to 192. And we're just in time for the new Cinebench 2024 benchmark, which, yes, this machine dominates. But it's not all perfection. The M2's individual cores are faster, and I didn't even mention Intel or AMD. They also do really well single core. And 128 cores can be overkill if your application can't use all of them. Ampere and ADLINK designed this system to be the ultimate ARM development workstation. And that it is. But I like doing crazy things. Can this also be a great gaming rig? Can the CPU break a teraflop? Can we install a 4070 Ti in it? And where did I even get this graphics card? From this video's sponsor, Micro Center. I bought some used ECC RAM for this upgrade, then Ampere went crazy and sent even more RAM and a 128-core CPU. But I was like, with all this power, I need better graphics. So I went down to my local Micro Center. The staff are always helpful getting me exactly what I need, and what I like even more is they have stock of, well, practically everything I'd ever need to buy, upgrade, or maintain a PC. They even have small business and enterprise networking gear, like they sell the Wi-Fi 6E AP I just installed that gets over a gigabit all wireless. Micro Center has everything you need for your next build, and they even have a PC builder so you can match up just the right components without ever leaving your home. And with their 18-minute in-store pickup, you don't even need to walk around and grab everything if you're in a hurry like I was on my Mr. Beast project. Head to Micro Center today and new customers can buy a brand new Ender 3 V2 3D printer for just 99 bucks. And this fall they have tons of other great deals on laptops, desktops, monitors, and almost everything you might need. Check them out below. Okay, so as of today, I have this thing running 128 CPU cores at 2.8 gigahertz. I upgraded the RAM to 384 gigabytes of DDR4 3200 ECC RAM, specifically 6 of these Samsung 64 gig sticks. I installed an Nvidia 4070 Ti. Well, it's really Ti, but I'm just going with Nvidia's pronunciation here, so don't shoot the messenger. It's running both Ubuntu 22 and Windows 11 for ARM now. I even got Steam installed on Ubuntu after so many of you kindly pointed out Box86 and Box64 exist. But before we get into full benchmarks and gaming, I want to talk you through the RAM and CPU upgrades, because I learned a lot about this platform. Like, did you know at a certain point, more CPU cores doesn't necessarily give you more performance, even on pure multi-core tasks? Yeah, and the main reason for that, memory is just not getting faster at the same rate as our CPUs. Have you ever seen one of these fancy server motherboards on Serve the Home? This is a new server for AMD's Bergamo CPU. Do you see how many memory slots are in this thing? There are 24. There's 2 memory slots for each of the 12 memory channels on the processor. That's a lot compared to a normal desktop where you might get 2 or 4 slots for RAM. What gives? Well, modern multi-core CPUs are getting faster and faster, but feeding them with data hasn't kept up. So big servers need more and more sticks of RAM feeding data to the individual CPU cores just so they don't sit around waiting. And RAM goes a lot deeper too. I'll link to a GitHub discussion with a lot more depth, but look at these 2 sticks of RAM. See how the one on the right has twice the number of memory modules? That allows the individual stick of RAM to pump through data more quickly than the one on the left, even though both of them are rated at DDR3200 and CL22. If you look really closely on the labels, you can see one is 1R by 4 and the other one is 1R by 8. Actually, hardware overclocking has a great video on this, but bottom line, this by 4 stick is about 30% faster than the by 8. I tested 3 setups, 96 gigs of Transcend RAM, 96 gigs of Samsung RAM, and 384 gigabytes of Samsung RAM, and I learned a lot about memory latency and bandwidth. But the most important thing I learned is this system design only exposes 6 out of the 8 available memory channels on this beefy CPU. So there's actually an upper limit to how much performance I can get just upgrading the CPU. This system's memory bandwidth tops out around 174 gigabytes per second. But you might get more with more memory channels. A lot of Ampere server builds do give all 8, and maybe I'll get one someday. But for now, I still wanted to test all 128 cores. For the upgrade, it's a little different than a normal desktop CPU. I popped off the water cooling block, which is normal, but underneath, I made sure to follow the open pattern for loosening the CPU bracket. I pulled out the 96-core CPU, and man, that is a lot of pins. I mean, on any of these modern EPYC or Xeon or Ultra systems, there's just an enormous amount of pins. In this case, for up to 8 memory channels and 128 lanes of PCI Express. That's just a ton of bandwidth. So in goes the 128-core CPU, and in my case, it's the 2.8 GHz version. They actually make a 3 GHz version, but since Ampere sent this thing to me for testing, and the overall efficiency is probably a tiny bit better at 2.8 GHz anyway, I'm not complaining. And yes, I'll show you how I applied the thermal paste here. Honestly, you can put it on however you want, as long as you verify the CPU temps afterwards. For this install, I pre-spread it with one of my little cases the memory came in. I plugged it back in, booted back up, and it posted at 2.8 GHz, so the next step was to boot into Linux and make sure I could see all 128 cores, which it did. Honestly, HTOP doesn't know what to do with so many cores here. But I ran my Linpack benchmark again, and on the 96-core CPU, it got around 1.2 teraflops, but I could still only get around 1.2 teraflops. After a ton of research, and after upgrading the system to 384 gigs of RAM, I could eke out about 1.3 teraflops, but it seems like that's the upper limit on this particular motherboard. Which, I mean, that's not bad at all, but if you put the same CPU in a server with all 8 channels of RAM, this thing should go even faster, probably past 1.5 teraflops. But if you really care about teraflops, you need a graphics card. Nowadays, more and more workloads can go way faster using a GPU, especially AI and machine learning. Not to mention games and design apps, and sorry Apple, but only allowing your own integrated GPU just doesn't cut it these days. I decided to go with an Nvidia 4070 Ti, and before you start yelling at me about not using AMD for a Linux first build, AMD's drivers on ARM aren't quite as stable yet. Nvidia making their own massive ARM processors probably has something to do with that, but in any case, I went with this understated ProArt GPU from Asus. It's not gaudy like most modern graphics cards, and it fits nicely in this case. I test fitted my 4090, but that thing's a monster, and it would also require this bigger power supply, which I also picked up from Micro Center. Maybe I'll upgrade to it someday, but for now, 4070 it is. Installation was easy. I just popped in the card and made sure to install the little support stick Asus includes. Now, before I could get anything out through the graphics card, I had to get drivers going. Ampere has a guide for the process, but basically I installed a desktop environment since I was running Ubuntu Server 22, then I installed the Nvidia drivers. I shut down the system, plugged my monitor into the card with HDMI instead of the integrated VGA port, and away it went. One thing to note is you won't get any of the early boot stuff like the BIOS screen through a graphics card. Those things still go through the integrated A-Speed controller, but everything else in the OS goes through the GPU now, and Ubuntu had no problems. I ran GLMark 2 and got a score of 10,260, and I also installed OBS and was excited to see NVENC hardware encoding worked without any extra setup. So I used OBS to record all the rest of my testing, and it worked without a hitch, allowing the GPU to do all the heavy compression for screen recordings. Next, I booted up Super TuxCart and got an easy 120 FPS with all the settings completely maxed out. I mean, this beat the pants off any other ARM system I've ever tested. I also installed Blender and messed around with a demo scene. The UI was responsive and rendering wasn't too painful, but I did notice Blender's CUDA support wasn't working. So the 128-core CPU could keep things moving, but I'm guessing a little more work is required for GPU acceleration. GPUs are also huge for things like ChatGPT or Llama, and it's easy enough to install Llama locally, so I grabbed a massive 13 billion parameter model and installed a web UI. The Ampere chewed through it as I asked a series of questions. It worked okay, but it could be a lot faster if I can get GPU support going. I had a little trouble, but again, it's probably not too difficult to get it working. It's just that not many devs working on the software have access to these fast ARM workstations yet. I mean, even without the GPU, large language models are certainly one way to utilize all 128 cores. It's also interesting to see this model already knows a lot about me. To round things out, I also played back a YouTube video at 4K 60, and there was zero issue there. Firefox seems to be using the GPU just fine. I rebooted into Windows 11, and things were a lot more bleak there. The GPU can be seen by Windows, but Nvidia only publishes ARM drivers for Linux, not Windows. So in Device Manager, you just see a basic display adapter, and it can't really do anything. And OBS runs in Windows, but only with software encoding. And Blender won't start at all since it requires OpenGL and a graphics card, neither of which Windows can get going yet on ARM. But Windows didn't have any problems with the CPU or the RAM. It picked up all 128 cores and all 384 gigs of RAM. I was excited because Cinebench just released their latest 2024 version, and one of the headline features is Windows on ARM support. They mentioned Snapdragon CPUs like the one that's in the Windows Dev Kit 2023 I tested last year. I booted up that system, and after waiting an hour or so for Windows Update to finish, I ran Cinebench and got 69 single and 435 multi-core. Just for fun, I also ran it on my M1 Max Mac Studio and got 111 single and 799 multi. On the Ampere, 47 single and 2,409 multi. That even beats the M2 Ultra, which gets a maximum of 1918 on the multi-core test. Now, the M2 Ultra is gimped a little bit. It only has 24 CPU cores. But I noticed the MP ratio is only 51 times on the Ampere. That ratio should be a lot higher, like at least 100 times. What gives? Well, I opened up Task Manager, and whether I ran the 96-core or 128-core CPU, and even trying the Enterprise edition of Windows on ARM, there was no way to get Cinebench to use more than 64 CPU cores. Windows used all the cores, it was just Cinebench that seemed to have an issue. If that gets fixed, we should be able to go way past 2400, maybe around 4000, but we'll see. I've been in contact with Maxon, and they now have access to some beefier hardware for testing. So Cinebench is one thing, but something a lot of people mentioned is I should try Minecraft on Windows, since there may be an ARM native version in the Microsoft Store. I installed the Java and Bedrock edition from the store, and, well, it ran. It wasn't quite playable, and it looks like it's trying to run the game on the tiny A-speed graphics, which can barely do 10 frames a second. But it's an entirely different experience on Linux. I installed Minecraft with Pi apps, and it ran beautifully. Zero issues getting 60 FPS. I can't get ray tracing on this version though. It's the one from the Google Play Store, and I don't think that edition has RTX support. Next, I also tried installing Steam and finally have that running. I followed Ampere's guide for installing Steam using Box86 and Box64, though I did have to tweak one install step to get the latest version. The main developer of Box86 actually has some Ampere hardware to test now too, and he's already fixed some emulation bugs while I was making this video. But anyway, with Steam installed, I started downloading all my games to see what would work. I made sure Proton was enabled, then booted up each game. CSGO installed and seemed to start launching, but it kept getting stuck in a boot loop where it would just die silently. Halo Master Chief Collection could launch and eventually get to a black screen, but it died every time with this little fatal error message. Portal 2 did the same thing as Counter-Strike, where it would just silently die every time I launched it. And despite the fact I got Crysis to run at like 1 frame per second on Windows, I couldn't get it to launch at all on Ubuntu. I tried Quake, but got an OpenGL error, and Need for Speed also died. Abduction gave me the same little fatal error Halo did, and Portal 1 also died. Finally, I tried Superhot, and that actually worked. It was nice and smooth, and, of course,
Super hot. Super hot.
Seeing some progress, I downloaded another older game, Horizon Chase Turbo, and got it running decently well, but only like 10 or 20 FPS. My lucky streak was over though, as I couldn't get Batman Arkham Knight to launch either, and Doom gave me this weird fatal error about some OpenGL function not being available. My luck was back though once I ran Kerbal Space Program. It seemed to run great and was plenty fast to be enjoyable. Blasting Jeb off in a rocket never gets old. This stuff is in very active development right now, so things will change. I highly recommend you follow Box64's development to find out if your favorite games could run on a dev workstation yet. I mean, gaming isn't at all Ampere's main goal here, but it's cool to see how quickly the community's made things work. And I'm glad Ampere and ADLINK have been supportive of getting more stuff running on their systems. And after all that testing on this workstation, I also set up a bare dev kit on my test bench. Ampere sent me this board with a smaller 64-core CPU, and I installed 96 gigs of RAM that I originally bought for the workstation, along with a Kioxia SSD and a Corsair power supply. And it runs actually a tiny bit more efficient than the full workstation, putting it squarely at the top of my top 500 efficiency ranking, outperforming even the Orange Pi 5. There are a few quirks to it though, like the main fan header isn't actually wired up, so you have to use an adapter to get the CPU fan working. And it only exposes 6 of the 8 memory channels like I mentioned earlier, so the highest end CPUs can't perform to their full potential. Finally, power consumption is about 3 watts powered off since it runs its built-in BMC for remote access, and booted up, it idles around 50 watts. But if you use it for anything that needs lots of CPU power and expansion, it's one of the most energy efficient computers on the market. These things are infinitely more upgradable than a Mac Pro while costing less than half as much, and I'm excited to see where ADLINK and Ampere take this platform in the future. This is a good start, and I think they could actually make a dent in areas even outside the workstation space, but we'll see. Right now, a lot of focus is on the even more massive Ampere 1 CPUs with up to 192 cores, DDR5 and PCIe Gen 5. Right now, this thing can't do media production like my Mac, but for all my other dev work, I could definitely be using this as my main computer. Links to everything down below, and until next time, I'm Jeff Geerling.